In this lesson, we want to talk about a property of surface integral on of a curl. If I have, basically, if I'm computing the surface integral of the curl of F on a surface, let's say S1, and S1 has the same boundary as another surface S2, then they're both are oriented the same, then I can say that the surface integral on S2 of curl of F dot ds is the same as the first surface integral. So what are we using here? We're using this fact, and we're using the Stokes theorem. And so Stokes theorem says that the curl of F dot ds, and the other way, if you remember, curl goes with the cross. So curl of F dot ds, or surface integral of curl of F on S1, is equal to the contour, correctly oriented contour line integral over the boundary of S1 F dot dr. And here also it's equal to the line integral on the boundary dr, according to Stokes theorem. And if the boundaries are the same, they're going to be the same. Now, how are we using this? Here I have this question. It says, consider the surface in R3, and this is the surface for z bigger than or equal to 0. And you have a vector field looking like that, and it's asking you to evaluate the curl, the surface integral of the curl. Let's take a quick look at the surface. I know that, yes, the parameterization is doable. I can go and brute force this, and I may use some techniques, or computing the surface integral is going to be very difficult. So I graph this shape, and that's what it looks like. And then I can see the boundary down in the xy plane, because z equal to 0 gives me the intersection of the surface with z equal to 0 gives me the boundary. And if I place this, this one is not given, the purple disk on the bottom is not given, but I can imagine I can cap the mouth of this surface with that purple surface. And that purple surface is the disk of radius. Let's go back here. It's, if I set z equal to 0, I get the disk of radius. So set z equal to 0 and get the boundary. And basically, or the plus 0 minus e to the power 0. So it's x squared plus y squared equal to 1. That's 0 minus 1. And so that gives me, in the plane z equal to 0, not in 3D space, in plane z equal to 0, this gives me boundary. It's a circle. So if I get the disk x squared plus y squared less than or equal to 1, that disk is the other shape that we saw over there. So my plan is to compute the integral over this disk, the surface integral over this disk. So first of all, let's compute the curl of F, and curl of F is equal to curl of F and that's I, J, K, partial respect to X, partial respect to Y, partial respect to Z of X squared Y and minus X, Y squared, X, Y, Z. And that is going to be XZ, negative YZ, and negative X squared minus Y squared. Now we're computing this curl in the outward direction on the disk of radius 1, right here in the XY plane. And so the upward direction is going to be, for this disk, is going to be just K. So if I dot the curl with K, I get negative X squared minus Y squared. Again, what am I doing? I'm computing the surface integral on S of curl of F. And this turns out, if we call this D, it's the same thing as computing that on D. And so that's basically computing and wait, I computed the curl of F dot K, and this is supposed to be the curl F dot the little normal vector ds on D. D is a two-dimensional circle, so let's just use that basically. So how do I compute on the domain? I'm sorry, not circle, disk. How do I compute a double integral on a disk? In the same way as usual, I either can parameterize it, or I can remember that in 2D we can use the change of coordinates, basically transformations. And the two of them turn out to be the same thing. So here, if I change the coordinates, I know that the function is minus x minus y squared, that's minus r squared, and then times r, that's the Jacobian, and dr goes from 0 to 1, d theta goes from 0 to 2 pi, and you compute this, I'm skipping that part, and you end up with negative pi half. You could have actually parameterized this, and you don't need to because it's again in XY plane, but parameterization would have given you the same answer, basically. You could have parameterized it as x equal to r cosine theta, y equal to r sine theta. But as soon as you parameterize the disk and z equal to 0, in 2D, you see that it's exactly polar coordinate transformation. So you don't, you can just use the polar coordinate transformation instead.